Okay, so hi, I'm Neta. I'm a master's graduate from Rachman University in Israel. I'm going to talk about Stackelberg strategies for weighted load balancing games. Okay, so first we're going to start with a short introduction about job scheduling games. Then I'm going to present our model of Stackelberg load balancing games. Next, we're going to show some theoretical results, heuristics, and experimental results, and conclusions. Okay, so what is job scheduling games? We have it's a game constructed of a set J of n jobs, which is our players. We have set M of M machines, which are the resources, where each job J in J has a certain weight Pj. Each job represents a selfish player, which attempts to optimize its own objectives. And the strategy space of each of the job is the machines, where each job can schedule itself on one machine. So unlike the traditional scheduling model, where the centralized utility assign the jobs, in a job scheduling game, each job selects its own machine. And also we have a profile, which is an assignment of the jobs to the machine. It's kind of the state of the game. Okay, so the cost that each job wants to minimize is the total load on the machine it is assigned to. And which the load is the sum of all the jobs are scheduled to this machine. Also, the cost is independent of the job order. For example, in this image, we can see on the lower machine, for example, the first one, that each job pays 12. Doesn't matter the order. The second one has each job pays 8, and the third one 9. So the most common notion of stability for these games is Nash Equilibrium. Um, it's basically a situation where no job can benefit from migration, meaning that if a job moves, it won't have lower cost than what it had before. So, for example, in the upper image, we have a situation where it's not a Nash equilibrium because the job of size 2 can move to the second machine and pay 10 instead of 12. And in the lower one, after the job moved, we have a Nash equilibrium because none of the jobs can move to another machine and improve their state. So how do we measure our equilibrium? Because we can have many costs for the equilibrium. So first of all, the cost of a schedule, it's also called the makespan, is the maximal cost of a job, which is also the load on the most loaded machine in the schedule. And social optimum is the schedule where the maximal cost is minimized, also called the minimum makespan. So our measurement is the price of anarchy, called POA, is the ratio between the minimum makespan in the worst Nash equilibrium and the social optimum. So, for example, we have here on the upper image the worst schedule for this game, a game with 2 machines and these 4 jobs. The cost in this game is 4 because it's the load on the most loaded machine. And on the lower one, we have the optimal schedule with the cost of 3. Okay. So the price of anarchy of this schedule is 4/3, which is also a tight bound for this instance for the price of anarchy in job scheduling games. This is a well-known bound. Okay, so what is Stackelberg load balancing game? Stackelberg was an economist that defined a leadership model for game theory. So in our model, it reflects in a way that we have a leader that controls a certain fraction of the load of the players. We have the game defined by a pair G, which is a load balancing game as we showed earlier, and alpha, which is the maximal fraction of control jobs. We have A is the set of jobs that the leader selects and control. So meaning that for the sum of all the jobs, the sum of the load in the group A is at most alpha P. So the game works in a way that first the leader assigns all the jobs in the group A, and next every job that is a selfish player, which is not in the group A, chooses its own machine. And also we define the matching measurement, which is POAL, price of anarchy with the leader. It's the ratio between the minimum make span in the worst Nash equilibrium for our setting and the social optimum. Also depends on the alpha value. So now we want to ask, first of all, can it help us to have a leader in the game? Will it improve the game cost? And also, how can it do it? What is the best strategy for the leader to act? So this one divides to two questions. First of all, how should the leader choose the control jobs? And second, how should it schedule them? So some related work. First of all, we'll notice that for the two extreme cases, we have the case that the leader controls all of the jobs, which will get the minimum make span problem. It's a NP-hard problem, well studied. There's many approximation algorithms for this. The second one is the case that the leader doesn't control any job, and then we just get a regular load balancing games as we presented, which for this, the price of anarchy is this value. And on Stackelberg games, so far they were studied on different models, not relevant to our model, for different kind of games and settings. Okay, so we'll start with some results. First of all, we checked what if the leader should exploit all of its power or not, meaning that it should control a maximal subset of the fraction alpha that it's allowed to control. So we defined the corresponding equilibrium mean efficiency, the measurement. And then we showed that there exists a game that actually forcing the leader to control the maximal set makes it worse than not having a leader at all. So in this case, we better not to have a leader. For the second result in this part we have, we showed that even if the leader controls a very large alpha, then it doesn't it can't guarantee that it can reach an optimal schedule. It also applies. It is valid even if the instance has only two job sizes. For example, in this image, we can see that for this game, every Nash equilibrium is optimal in a leader-free games. But if we force the leader to control the maximal alpha, it may choose this like dark green subset, and we can get a non-optimal schedule. Okay, and next we have some, we showed some relations between price of anarchy and price of anarchy with the leader. We identified the threshold over the values of alpha that where a leader can improve a game state. And another case we considered is for the leader to choose a certain number of jobs. We showed that also for this case, the leader can guarantee that we can guarantee benefit from having a leader. Okay, next we have in the remaining time, we have some heuristics and experimental results. We first start from choosing the control jobs. I'll remind that we have two parts for the leader's role. We have choosing the control jobs and scheduling them. So here we consider the three heuristics. We have the pick smallest, where basically the leader just selects in a non-decreasing order jobs until it reaches the alpha P. We have pick largest, stop, and skip. In both, the leader will go over the jobs in non-increasing order. Where in stop, it will stop once stop adding jobs once it can't fit the alpha P value. And in skip, it will continue going over the jobs until the end, while it can still add to the alpha P. So for example, we have a group of jobs, this 1, 2, 3, 4, with a total value of 10. Our alpha is half, meaning that the leader can choose to control at most 5 of the load. So in pick smallest, it will go over the smaller jobs. We'll choose 1 and 2 since 3 can't fit anymore. In pick largest skip, it will go over from the largest and keep going. So meaning it will choose 4 and then it can't fit 3 and 2. So it will also take to control 1. And in pick largest stop, it will take only 4, this job, because the 3 is going over the alpha P value. Okay, so next, how should the leader schedule the jobs? We first consider the leader's LPT, longest processing time, same as the known algorithm. It will sort the jobs in non-increasing order and assign the jobs to the least loaded machine. The second one we have is the leader's first fit based on a bin packing problem. So we define the value L, which is a bound over the optimal value of a schedule. And we define the bin's capacity, which are basically our machines, to be gamma L, we consider the 3 gamma values. Then the leader sort the job in non-increasing order and use first fit algorithm to schedule the control jobs, which basically means that it will go a machine one after another and add jobs while it still can, while it still fits the capacity. For example, we have here this set of jobs with a total load of 20. We have 2 machines. So our L is approximated, is the bound on the optimal schedule, is 10. We have alpha is 0.75, and the group of control jobs is 6, 5, and 4. So for gamma equal 0.9, we have the leader will consider adding the first job to the machine and it will add it. The second one can't fit gamma L, which is 9, so it will put it in the second one. And also for the next one, it can't fit 9, so it will schedule it on the next machine also. Same for the alpha other gamma values. Okay, so once the leader completes assigning the control jobs, the selfish jobs join the schedule. So we should also need to consider the selfish player's strategy. We have first player's LPT, which is same as we showed leader LPT, just schedule in a non-increasing order on the least loaded machine. And we have a BRD, which is the most common way to reach the most common algorithm for Nash equilibrium. We use a round robin according to the job's assignment order. And it's basically a local search method in which the players in its turn can change strategy at a time. Also, it is known that the BRD conversions to Nash equilibrium. So we'll go over very quickly on some experimental results. Each figure, we measure the average make span of the resulting heuristic compared to a theoretical bound of a perfectly balanced schedule. We first see here that as for the chosen control job strategy, pick smallest did the worst results because we want a lower value. So pick largest, stop and skip did very similar results. We also compare the results for the different gamma values for a leader's first fit. And finally, we compare the both of the algorithm, leaders LPT and first fit in both of the players' strategies. The most significant thing we can see here that as a rule, as alpha increases, we have better results. So we can say that it's beneficial to have a leader. Okay, so to sum up, first we have our contributions is that we defined the model of Stackelberg weighted load balancing games and the measure of POAL. We showed that controlling the maximal amount of the given fraction may be worse than a Nash equilibrium schedule in a leader-free environment. We also presented some tight bounds on the fraction alpha of the controlled load that may improve the game cost. And we saw also some relations between the common price of anarchy and price of anarchy with the leadership. And finally, from the experiments, we have many more conclusions in the paper, but what we saw is that controlling the largest jobs in the game is the best strategy for the leader. And the smallest job can even cause damage on the results. In the case where we control smaller jobs, we better not to have a leader in the game. And finally, that controlling the larger fraction of the load improves the game cost when controlling the largest jobs. And thank you.
Thank you for your presentation.